So far in maths, you've only learned one way to measure angles, which is degrees. I don't think I really need to go over this. So this here is 30 degrees, this here is 90 degrees, this here is 180 degrees where it's a straight line, and this here is 360 degrees where it goes all the way around in a circle like this. There is another way to measure angles, and this is called radians. Now, you've probably never met these, and a lot of people find these quite complicated, including myself. I do a science degree at uni, and radians comes up a lot, and it still confuses me sometimes. So we'll go through them slowly. Radians is measured in multiples of pi, with 360 degrees being equal to 2 pi, like this. Or another way to remember it, 180 degrees is equal to pi. And everything is based around this. So we can see that 180 degrees is equal to pi, and 360 is double of 180. So therefore the radians are double too. So it goes from pi to 2 pi like this. This is the same for 90 degrees. So 90 is half of 180. So therefore in radians it will be half of whatever it is in radians at 180 degrees, which is pi. So 90 degrees is equal to pi over 2. You can also write this as half pi if you want to as well, whichever one you prefer. They're the same thing, they're both acceptable. So what would 30 degrees be? Well, 30 is a third of 90, so therefore in radians it's going to be a third of pi over 2. So it's going to be pi over 2 times a third, like this, which is going to be equal to pi over 6. So 30 degrees is equal to pi over 6 radians. And that's basically how you figure out radians. You start with 180 degrees is equal to pi, or you can do it for 360 degrees is equal to 2 pi if you want. It doesn't matter. I just find it simpler to do 180 degrees is equal to pi. And then you figure out what the radians are relative to what the fraction is of 180 degrees. Now, degrees, as you know, have this symbol here to denote degrees. Radians are written with rads on the end, like this, to show that it's radians, but a lot of the time we don't actually bother writing this. We can just write it as pi over 2, and that's perfectly acceptable. I will use this rad thing in this video here just because we're going to be using both degrees and radians, so therefore we can distinguish between the two. But a lot of the time, if we're writing down an angle in radians, we don't bother writing down this rad thing. We just write down pi over 2, for example. Really quick, what do radians actually mean? Where do they come from? Well, as it's got pi in it, you can probably guess it involves circles somehow, and it does. So if we have a circle with a radius of 1, like this, its circumference will be equal to, hopefully remember this from the basics of circles, is equal to 2 pi r, and as the radius is 1, therefore the circumference will just be equal to 2 pi. Remember, the circumference is the edge around the circle, like this, the length of it. So the circumference is 2 pi. And we sort of consider the whole circle to have an angle of 360 degrees, because remember 360 degrees goes the whole way around the circle, and you can see that 360 degrees covers the entire length of the circumference of the circle. So therefore this is where this relationship of 360 degrees is equal to 2 pi comes from. 360 degrees is this, and the circumference is 2 pi. If we take separate sections of the circle, such as half of it like this, so therefore we make a semicircle, this angle here will be 180 degrees, and we can see that this covers half the length of the circumference, which is going to be pi. So therefore 180 degrees is equal to pi, and so on and so forth. This is where this relationship comes from. To convert between radians and degrees, there are formulas that you can use. So to go from degrees to radians, it's going to be degrees times by pi, and then divided by 180, like this. And then to go from radians to degrees, the radians need to be times by 180, and then divided by pi. You can see that these two are just the opposites of each other because degrees and radians are the opposites of each other. These aren't given to you in the formula booklets. So here's some examples of going from degrees to radians like this. So let's start with 60 degrees. Now, when doing degrees to radians, I personally don't remember or use this formula here as it isn't given to you in the formula booklet. And I don't really like remembering formulas. All I do is remember that 180 degrees is equal to pi. Just remembering this and then finding out what the radians are relative to this, sort of how we did it at the start. So let me show you again what I mean with 60 degrees. Let's convert this into radians. So 180 degrees is equal to pi, and we know that 60 is 1/3 of 180. You can do it like this if you want and put it into a calculator if you want. 60 is 1/3 of 180, and as we know 180 degrees is equal to pi, therefore 60 degrees is going to be 1/3 of what this is in radians. It's 1/3 of 180, so it's going to be 1/3 pi like this, and then this is the answer. It's 1/3 pi radians. Again, you can write this as pi over 3 if you want to. This and this are the exact same thing, it just depends which way you like to write it. I interchange between the two a lot, and that's how I do it. I know I have essentially used this formula here, but I've done it more just by knowing that 180 degrees is equal to pi rather than remembering this quite clunky formula here. So that's the way that I do it. So let's do the second one, which is 120 degrees, and we know that 120 is 2/3 of 180. Again, you can just do it like this if you want to. So therefore it's going to be 2/3 pi radians like this. So for the third one, it's 135 degrees, and 135 is 3/4 of 180. So therefore it's going to be 3/4 pi like this. Again, you can write this as 3 pi over 4 as well if you want to. It doesn't really matter. So for the fourth one, we've got a negative angle here. Now I know we can't actually have a negative angle in terms of what we saw in the circle beforehand, but we can have a negative angle if you think about solving trigonometric equations like we did in year one. You can have negative angles because remember a sine graph, for example, it has both a positive part but it also has a negative part as well. So you can have negative angles. So 30 is 1/6 of 180, so therefore minus 30 is minus 1/6 of 180, so therefore it's going to be minus 1/6 pi radians like this. 450 degrees, which is bigger than 360, and again you might be thinking that you can't have an angle bigger than 360, but again if we're talking about solving trigonometric equations and in terms of sine graphs and things like this, sine graphs go on forever, so therefore you can have any angle basically as a number. So you can have this angle here that's bigger than 360, and the way you just do it is just by doing 450 divided by 180 is equal to 5/2, so therefore it's going to be 5/2 pi radians. 450 degrees in radians is equal to 5/2 pi like this. And then for the final one, 54.7, so we just do the same thing. 54.7 divided by 180, if you put it into your calculator, is equal to 0.304. Now the only difference with this one, the reason I've specifically included this one, is we don't write this as 0.304 pi like we have with the previous ones. We only do this if we have fractions. If we've got a decimal, what we actually do is we times this by the pi here in order to, if you put it into a calculator, you'll get 0.955 here, and then we write it as this. So it's going to be 0.955 radians like this. And then once again, as I said before, I've written the rad here because we're talking about both degrees and radians and I want to distinguish between the two, but a lot of the time we don't bother writing this rad here. It's really not necessary. If you just write these pi values here, it's perfectly acceptable. And then here's some examples where we need to go from radians to degrees like this. Now here you do kind of have to use this formula. The technique basically is just times it by 180 and then just get rid of the pi, so we're dividing it by pi, so it will just cancel out. So for this first one here, it's pi over 4 rad. So basically remember this can be written as 1 over 4 pi like this. So just get rid of the pi and then just times the 1 over 4 by 180 like this, and if you put this into a calculator, this is equal to 45 degrees, and then that's the answer. So for the second one, it's pi over 5 radians, so therefore it's just going to be, again, just get rid of the pi to make it 1 over 5, and then times that by 180 to get 36 degrees. And then for this one, 5 pi over 4, so again just get rid of the pi to make 5 over 4 times 180, which if you put into a calculator again is equal to 225 degrees. For this final one here, again you need to times it by, so 372 times 180 like this. As this is a decimal, as we talked about before, we don't write it in terms of pi like this, we actually times it by pi and it's included in this. So for this one, because there's no pi here, we can't just cancel out the pi, we're actually going to have to divide it by pi and put it into our calculator, because this value has been multiplied by pi to get the radian value. So therefore it's 0.372 times 180 divided by pi, follow the formula, and this is equal to 21.31 degrees. So you might be wondering at this point, why do we actually need radians? Why don't we just use degrees all the time? This isn't just a cruel way to make new questions at A level. We have to use radians in differentiation and integration. We have to use radians in trigonometric functions such as sin, cos or tan instead of degrees when we are differentiating or integrating. We will see why this is in chapters 9 and 11 of year 2. But let's have a look at radians in trigonometric functions. So for example, what is sin of pi over 6 radians like this? Well, pi over 6 is equivalent to, so we just did this, so pi over 6 radians, if you want to put it into degrees, you just get rid of the pi, so it's 1 over 6, and then times that by 180. So therefore, if you put this into a calculator, it's equal to 30 degrees. So as pi over 6 radians is 30 degrees, therefore sin of pi over 6 radians is going to be equal to sin of 30 degrees like this. These are the exact same, they're just in different values of radian, different units of radians and degrees. And sin of 30 degrees, either if you know it off by heart or if you just put it into a calculator, gives out the value of a half. So sin of 30 degrees is equal to a half, and therefore sin of pi over 6 radians is also equal to a half here. So that's the way that you can figure out trigonometric values in radians. You can do what we just did there, convert it into degrees and then put it into your calculator and figure it out. Or you can directly put the radians into your calculator. So on your calculator, if you press shift and then the menu / setup button, it comes up with these options. If you press the number 2 for angle unit and then press the number 2 again for radians, your calculator will now be put in the radian mode. And now if you put sin of pi over 6 directly into your calculator, it will come out as a half. It didn't do that before. Now note, this is the only thing the radian mode does. It doesn't change any other thing that your calculator does. All it does is for the trig values that you put in, they will now be in radians instead of degrees. You can easily change this back by doing what we just did again, but when you get to that same screen, press 1 for degrees instead. You can tell what mode your calculator is in by these little letters up here. If it's in degrees, the D will be lit up, and if it's in radians, the R will be lit up. Now this is very important, and be careful with this. When you're doing trig values in your calculator, check what angle unit your calculator is in. I've got questions wrong before because I was putting, say, pi over 6 into my calculator trying to do radians, but my calculator was in the degrees mode and I didn't realize, so it gave out the wrong value. So this is especially prevalent for some values, like I randomly found for 3.1. The values that you get out if your calculator is in radians and degrees are quite similar, and it's very hard to tell apart, if you can see. But if you put the wrong one down when you write it down in your answer, you are going to lose marks. So always check that D and R letter at the top so you know what mode your calculator is in, and to make sure that you're working in the right one for that specific question that you need. So So here's just two more examples. If you put cos of pi over 10 radians into your calculator, as long as it's in the radians mode, it will give out the value of 0.9511. As well, if you do tan of 1.25 radians, it will give out the value of 3.0096. Finally, I just want to talk about trigonometric graphs involving radians. There isn't really too much to talk about here, but here's a question they could ask you to sketch the graph of y is equal to sin x in the interval 0 to 2 pi. Now, we've talked about trigonometric graphs in chapter 9. Go back to that video if you need a refresher. This is the exact same, but now the interval units are in radians, and as 2 pi is equivalent to 360, the question is to sketch the graph of y is equal to sin x in the interval 0 to 360 if it was in degrees, but it's in radians, so therefore we need to do the units of the graph in radians as well. So we need to sketch the graph of y is equal to sin of x. So remember, it starts from 0 and then comes up like this here, and then comes down to 0, and then it goes negative like this here, and then comes back up to 0 here. This here is 0, this here is 1, and this here is -1. Now normally this would be 0, this would be 90, this would be 180, this would be 270, and this here would be 360. But with this question, because the interval is in radians, therefore we need to do the roots in radians as well. We need to do the x-axis in radians, so therefore it's going to be 0. Instead of 90, it's going to be pi over 2, and instead of 180, it's going to be pi, and instead of 270, it's going to be 3 pi over 2, and instead of 360, it's going to be 2 pi like this. Remember, you have to label the these points here when you're doing the trigonometric graph. And this is the graph of y is equal to sin x here. So these are the sin, cos and tan graphs between -2 pi and 2 pi, aka -360 and 360 degrees. And again, you can see that these are the exact same as we're accustomed to, except the x-axis is now in radians and not degrees. And the reason I'm showing this is because of something else I talked about in year 1, which was periodicity. Periodicity is the idea that trigonometric graphs repeat themselves. So for sin and cos, you can see that this happens every 2 pi, aka every 360 degrees. So for the sin graph, you can see that it has this shape over 2 pi, and then it repeats itself for the next 2 pi, and it will go on and on. And for y is equal to cos x, it's the same. Over 2 pi, it has this shape. It has this shape again, and it will repeat itself like this. And for tan, this happens every pi, aka every 180 degrees. So it has this shape for pi, and then for the next pi radians it has this shape, and then for the next pi radians it has this shape, and then so on and so forth, and this repeats itself forever. And as a result, we have multiple radian values that give out the same y values. So for example, for the sin graph, at a half, which let's say is about here, so let's say this is a half, we see that we have a value here, and this is pi over 6, which we talked about before. Sin of pi over 6 radians is equivalent to sin of 30 degrees, which is a half. But if we extend this, as we have done here, we can see that there is another value for which it is a half. I'm not going to talk about this too much here, as we talked about it in part 1 of the simple trigonometric equations video in year 1, and I'm going to talk about it again in the trigonometric equations involving radians video in this chapter as well. But we can find this value here because trigonometric graphs are symmetric. So this here is pi over 6, and this here is 0. So the difference between this here is pi over 6, and this here is pi, and we know the difference because it's symmetric. This is also pi over 6. So therefore this value here is going to be pi minus the difference here of pi over 6, which is equal to 5 pi over 6. So sin of 5 pi over 6 radians is also equal to a half. You can put this into your calculator in order to confirm it as well. I'll talk about this more in the trigonometric equations video in this chapter. Finally, they could also do transformations of radian graphs as well. Now, we talked all about trigonometric graph transformations in a year 1 video, so go back to that if you need a refresher. This is the exact same thing, except now the x-axis is in radians instead of degrees, but the principle is the exact same. So in that video, I talked about the best way to do it is to first sketch lightly the untranslated graph. So that is going to be y is equal to tan of x, and then therefore base your transformation on that. It's just quite a useful template in order to base it off. So y is equal to tan of x looks like so. It comes up from 0 here like this, and then it comes down like this, and then it comes down from pi like this, and then up like this here. Now this has asymptotes which we normally would draw in. The only thing with when you're translating tan graphs is we're going to have to draw another set of asymptotes for the translated graph, and we're going to be therefore drawing asymptotes on top of asymptotes, and that's going to get quite messy quite quickly. So as this isn't the actual graph that we're getting marked on, this is the graph here that we're getting marked on. I'm not going to draw in the asymptotes for this one, so we'll draw in the asymptotes for the other graph. Y is equal to tan of 2x. So you can see compared to tan of x that this is an inside the function stretch. So remember, when it's inside the function, go back to transformations if you need a reminder. If it's inside the function, it has the opposite effect of what you're expecting. So it's going to squeeze the graph by 2 in the x direction. So this here is going to come up, but instead of coming up to pi over 2, have an asymptote pi over 2, it's going to have an asymptote pi over 4. It's going to look like this here, and then this is going to come down to minus pi over 4, like this, and then this is going to come up from minus pi over 2, like this, here, and then this is going to come down like this here, and then this is going to come up like that. Then this is going to come down here. This is going to come up here. And then this is going to come down here. Now let's sketch in the asymptotes for this one. So the asymptote is going to be here, 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 and here. And we're going to sketch the new coordinates of where this asymptote here, which is pi over 4 here. This here is going to be 3 pi over 4. This here is going to be minus pi over 4. And this here is going to be minus 3 pi over 4. And then this is the graph of y is equal to tan of 2x here. So I know it's really messy, it's really hard to do this on a drawing tablet. So draw in the asymptotes when you're doing a tan graph, and make sure you label the new points of where the asymptotes are. So here's another example where we need to sketch the graph of y is equal to tan of x plus pi over 2 in the interval 0 to 2 pi. So if you want to work in degrees in your head, if you find it easier, this is the interval of 2 pi is 360, like this. And we need to do a translation of pi over 2, and pi over 2 is 90 degrees, if you remember. So if you want to work in degrees in your head, that's fine. So we need to sketch this graph here. Now, I talked about previously how it's always good in order to sketch the untranslated graph, so it'd be y is equal to tan of x, because therefore you can kind of use this as a template. Just to save time in this video, I've already done this. So it's an inside the function translation, so that means it's going to have the opposite effect of what you're expecting. So it's going to shift everything to the left by pi over 2, despite the fact it's got a plus. So this here, remember, it's good to use this as a template because you can see where everything's meant to go. So this here is going to come here, and therefore this is going to come here as well. So this is going to come down like this here. So remember, everything's shifted this way by pi over 2. So now this is going to come up here like this. This here is now going to become here. So it's now like this because everything comes this way by pi over 2. And then this comes up like this here. So this is the graph, remember, drawing the asymptote. So there's one here, and there will also be one here. I know you can't see it because we haven't drawn the other side of this interval, but there will be an asymptote here, and there will also technically be another asymptote here as well at 0. So this is the graph of y is equal to tan of x plus pi over 2. Very finally, they could ask you to do multiple transformations. So here's an example that's actually specifically mentioned on the spec, where they want you to sketch the graph of y is equal to 3 plus sin 2x in the interval 0 to 3 over 2 pi. So in degrees, this is the interval between 0 and 270 degrees like this. I've already drawn the untranslated graphs, the template, y is equal to sin of x here. Now, with multiple transformations, I've already done a video on this, so go back to it if you need to. With multiple transformations, you need to do each transformation individually, and the order in which you do them is the order in which the transformations affect x. So you can see that this 2 will take effect before the plus 3 does, because it's inside the trigonometric function. There's technically a bracket here. So therefore, we need to do the y is equal to sin of 2x transformation first, and then we do the outside the function plus 3. So do the inside the function first and the outside the function second. So we need to do this transformation. It's an inside the function stretch, so therefore it's going to squeeze everything by 2 in the x direction. So therefore this here, this maximum, is now going to become here. So it's going to come up like this to here, where this is at pi over 4, and then this root here at pi is now going to be at pi over 2, so this is going to come down here to here at pi over 2, and then this here at 3 pi over 2 is now going to be at 3 pi over 4, sorry, this minimum here. So this is going to come down like this here, and there's going to be a new root that we can't actually see here that's going to be like this here, and then there's going to be a maximum here at 5 pi over 4 now. So you can see pi over 4, 3 pi over 4, 5 pi over 4, and then this is going to come down here, and there's going to be a root here, and you can see that the graph is squeezed. We still have the same shape, but it's now squeezed by 2 in the x direction. So this is the graph of y is equal to sin 2x. Just for the purposes of this video, I've removed the grey y is equal to sin x curve, just because it's a very small axis, and if we plot 3 curves on this axis, it might just get a bit messy and unclear. But it's perfectly fine to leave it on there on exam paper or anything like that. I also need to extend the y axis as well. So now we need to do this transformation here. So it's the y is equal to 3 plus sin of 2x. So we need to do the 3 plus. This is an outside the function translation, so everything's going to get shifted up by 3. And the best way to do this is to look at the axis and see what's going to happen. So this one maximum is now going to be a 4, and then these roots here at 0, you're plussing 3, so they're going to become 3. And this minimum at minus 1 is going to be minus 1 plus the 3, so it's going to be 2 here. So essentially the kind of the new x-axis is going to be at 3 here. So what's going to happen is at pi over 4 we have the maximum at 4, as we just said, which is going to come down here to 3, and then it's going to come down as well at pi over 2 like this, and then it's going to come down to 3 pi over 4. This is going to be shifted up by 3, so it's going to be like this here. Then this is going to come up like this at pi, and then this maximum here at 4 is at 5 pi over 4. Like this, and then it's going to come back down to 3 pi over 2 here. It does look a bit strange because of without the x-axis. If you add the x-axis back, it will look a lot more. It will look a lot more normal in terms of what we're used to here. And then this is the final graph with the y-intercept now being at 3. So this is the graph of y is equal to 3 plus sin of 2x. So here's another multiple transformation question that's specifically mentioned on the spec, where we need to sketch the graph of y is equal to minus cos of x plus pi over 4, where pi over 4 is 45 degrees, if you want to think about it in degrees, in the interval 0 to 2 pi, so it's going to be 0 to 360 degrees, if you want to think about it in degrees. So I've already sketched the untranslated graph of y is equal to cos of x, and as we said before in multiple transformations, the order in which we do the transformations is the order in which it affects x. So this is in the bracket, the pi over 4 plus pi over 4, so this is going to have an effect before the minus. So we're first going to sketch y is equal to cos of x plus pi over 4 like this. So this is an inside the function translation, so it's going to shift, it's going to have the opposite effects of what you're expecting. It's going to shift everything to the left by pi over 4 or 45 degrees. It's going to shift everything to the left by pi over 4. So we can see that this here, which is at pi over 4, is going to become the new y-intercept here. And we can also see that this root here at pi over 2 is going to be shifted to pi over 4, so this is going to become the new root. And we can see that this maximum, which was at pi, is now going to be at 3 pi over 4 as you take away pi over 4. And then this root here is going to come here at 5 pi over 4, as it's 3 pi over 2 minus pi over 4. And then this maximum here is now going to be moved to here to 7 pi over 4, and therefore we can do the sketching based on this. So it's going to start from about here, so about here, down to the root here at pi over 4, and then the maximum is going to be here because it's shifted from here, so it's going to come down like this to about here, and then the new root is being shifted to here, so it's going to be like this here, and then this is maximum is now here, so this is going to come up to here, and then we're going to start to see this come down here like this, and then this is the graph of y is equal to cos of x plus pi over 4, and we can see that we've got a new y-intercept. Now remember, the y-intercept is when x is equal to 0, so if you sub x is equal to 0 here, it's going to be y is equal to cos of 0 plus pi over 4, which is going to be pi over 4, and cos of pi over 4 is equal to root 2 over 2. So this new y-intercept is going to be root 2 over 2. So I just wanted to clear some space to make it a bit less messy for the next bit. And now we need to do this transformation here, y is equal to minus cos of x plus pi over 4. So this is an outside the function mirroring, so this is going to, if you remember, it's going to mirror it in the x-axis here, so this whole thing is just going to be mirrored in the x-axis. So this here is now going to be here, and it's going to come up to here like this, and then this here is now going to be here, so this is just going to come, maximum's going to be here still, so it's going to be like this, the maximum's going to be at 1, and this is going to come down to here, and then we're going to see this shape on this side as well, so it's going to come down to minus 1 at the minimum, and then we're going to start to see this come back up again until until the interval at 2 pi. So this is the graph of y is equal to minus cos of x plus pi over 4. We've already sketched in the roots from before and the x-axis, the x-coordinates for where the maximum is. We've got a new y-intercept here, but it's just going to be, as this is root 2 over 2 and it's just a mirror in, this is therefore just going to be minus root 2 over 2 here. And then that's the final answer.